A spinning wheel on a fireworks display is initially rotating in a counterclockwise direction. The wheel has an angular acceleration of negative 4.00 radians per second squared. Because of this acceleration, the angular velocity of the wheel changes from its initial value to a final value of negative 25.0 radians per second. While this change occurs, the angular displacement of the wheel is 0. Find the time required for the change in the angular velocity to occur. The text uses the sign convention that rotational motion is positive when it is counterclockwise and negative when it is clockwise. This convention applies to angular displacements, velocities, and accelerations in this chapter. It is important to note, especially as you encounter examples and problems in chapters 8 and 9 of the text. Note the similarity of this problem to that of a ball being thrown vertically upward, coming to a momentary halt, then falling downward to its initial position. Here is a drawing of the spinning fireworks. It is shown as it is initially spinning counterclockwise. The fireworks have constant angular acceleration that is clockwise. This causes the fireworks to slow down, come to rest for an instant, then reverse direction and spin counterclockwise with increasing angular speed. Our goal is to determine the time it takes to make this reversal. Let's begin our solution by filling in our table of known values. The spinning fireworks have an angular acceleration, alpha, of negative 4.00 radians per second squared. The minus sign indicates that its direction is clockwise. The final angular velocity is also clockwise with a value of negative 25.0 radians per second. This has the symbol omega. We are told that during the change in angular velocity that the angular displacement theta is 0 radians. The unknown variable to find is the elapsed time during which the change in angular velocity occurs. This is labeled t. The spinning wheel of fireworks is rotating with a constant angular acceleration. Therefore, we can apply the equations of rotational kinematics. On the left-hand side of the screen, we list the 5 rotational kinematic variables. 3 of these are known: the angular acceleration, the angular displacement, and the final angular velocity. The initial angular velocity and the elapsed time are unknown. We can consult Table 8.1, which lists the equations of rotational kinematics. Since we are interested in finding the elapsed time, we have a few choices of which equation to use. We'll use equation 8.4. This equation can be solved for the elapsed time, which is shown as equation 1 on the right-hand side of the screen. We still have one parameter, the initial angular velocity, that is unknown. Here is a hint on how to find the elapsed time during which the angular velocity is changing, t. Return to Table 8.1 to find a second equation that will enable you to find the value of the initial angular velocity. Then substitute that value into equation 1. When you complete these steps, you'll have solved the problem.